Hi everybody, thanks for being here. Today I'm presenting my graduate project, the Sonic Mudfish Errant Machine Learning for Reactive Generative Synthesis. So what does this mean? For this project, I designed and built a perceptron-based synthesizer for use in non-idiomatic electroacoustic improvisation. A perceptron is the simplest form of artificial neural network, which is a very popular strategy for machine learning and artificial intelligence. In general, the system works through two phases of machine listening and data derivation. With the data gathered from these phases, it excites a 231 perceptron. Then the system is able to sort of look into audio effects parameters and generative music structures that occur throughout the machine and gain a level of reactivity, thus feeling as though you're collaborating with the computer itself. The Mudfish is built using a Bella Mini microprocessor, essentially a small Linux computer, and is programmed using the Super Collider programming language. Before we get into my specific implementation of the neural network, I think it's useful to talk about what machine learning is, what AI is in general, just to make sure everybody's on the same page. Machine learning and artificial intelligence obviously connotes an extremely wide variety of technology. There can be some confusion about what this actually means. For this reason, I think it's useful to split it up into four categories. Reactive machines, which are machines that respond to any input stimuli. Limited memory machines, those that have an understanding of historical data or present history. Theory of mind machines, those with an understanding of the user's emotions and potential goals. And self-aware machines, those that have their own emotions and goals. Importantly, the latter two of these, though being the machines that are connoted most commonly by use of the term artificial intelligence, are purely theoretical. They don't actually exist. Rather, usually when you hear the word AI, it's a reactive machine or a limited memory machine. For this reason, a lot of researchers question what the difference between an intelligent system and a computer program is. I'm afraid I don't have a great answer on that. It is an active area of debate, but my personal opinion is that with human intelligence being a poorly understood subject, machine intelligence is a very metaphoric concept. This is sort of the problem that I'm interested in exploiting in the Mudfish. A neural network is the specific type of algorithm that I implement in this system. The way that these work is they function through node-based calculation of weighted sums. This is loosely based on the way that the brain processes information, and we can think of this as expressed in this formula right here. Summed data equals any amount of inputs, which are multiplied by unique multiplicative coefficients. From here, the summed data goes into an activation function, essentially a compressor for the data that biases it to a unipolar 0 to 1 range. This happens in every node in a network, which we can see laid out here. Every node would implement a weighted sum into an activation function, thus performing iterative data processing. At the output layer, a final value is produced, which can then look back into other parts of the network and update the weights, thus constituting machine learning or training the network. This is how I specifically implement a neuron in the Mudfish. I use Super Collider's SynthDef architecture to do so. I'm not going to go through line by line on this, but the specific lines that are of importance to understand how this works from a general standpoint. Right here, we see calculation of the weighted sum, two inputs, which are defined up here, and a bias. This goes into a sigmoid computation, which then does four things. One, it manipulates a comb filter, which is a simple form of a delay line. It also outputs audio twice, once to the master bus of the system, once to the audio processing within the perceptron, and once as data to the other nodes in order to perform this learning step. Up here we can see delta rule updating, constituting learning in the system. Once I reached this point in the project, I had to take a step back and think, I noticed that the neural network was extremely good at extracting patterns from data, but was less good at musically meaningful predictions with this data. And I found that application to music technology was extremely varied for this reason. I noticed somewhat of a spectrum. On one end, Google's NSynth. I call this the pure research approach, and that they use an algorithm to just do 4-axis vector-oriented synthesis. a pre-existent synthesis approach. They use a neural network to do this. On the far other end of the spectrum, David Tudor had built a neural synthesizer in the 80s with Intel. And the neural network is implemented on an integrated circuit as op-amps, which are essentially connected into each other to form a no-input mixer. I call this the errant machine learning approach, in which you do use the algorithm, but you fracture it in a way, you break it such that you reveal interesting sonic intentions. Specifically, my artistic goals in this were first to build a hardware-based interactive music system, that being a system that exhibits any changing behavior in response to human input. I wanted to develop a personalized approach to computational collaboration. In this way, I specifically biased the system to create derived sonic textures with the input data. This is ultimately realized as reactivity within the perceptron. Throughout the project, I wanted to make sure that this system lent itself well to chaotic sounds, unpredictable sounds, and this idea of any sound as a musical resource. I call this a non-idiomatic approach. Of course, use of the term non-idiomatic is problematic in a lot of ways, but I use it because rather than being concerned with extracting pitch class or rhythm from audio input data, I'm interested in whatever sounds the computer will give me from the neural network as a valid collaboration. Extending John Cage's assertion that sound should be allowed to be themselves, I'm experimenting with the idea of allowing an algorithm to be more of itself through less musically oriented mediation. This way I question, what can I learn about AI systems from this? I call this a post-digital approach to data sonification. Sonification because you learn from listening to data, post-digital because you learn from breaking and reassembling technology. In this way, I take the neural network algorithm and build it from the ground up. This video is around 4 minutes, but it does demonstrate some core functionality of the synthesizer as well as some improvisational exercises, and I think it will be helpful for contextualizing the machine. Here's a quick schematic of the system itself. Over here, we can see the potentiometers, those being the knobs that you saw on the system. Switches, buttons going to the digital inputs of the computer, the LEDs that you saw on the bottom, also that multi-touch sensor that can take up to 5 inputs at once, controlling the synthesis algorithm. This is the bill of materials. I won't go through this line by line, but I think it is fun to know that these are the different electrical components and supplies that went into building this. This is the probably most bird's eye view of how the code works. It starts with a mode switcher asking, do you want synthesized or externally input audio? This is that far right switch that you saw in the video. From there, it'll output this audio to a machine listening phase. That phase will extract amplitude, pitch, spectral flatness, and spectral centroid from the audio. These derivations excite the perceptron as data and as audio through the neuron architecture. Therefore, audio and data feedback through the system, and then feedback for the learning phase, acting as a no input functionality. This way, I treat the network as a sonorous digital structure and control source for other parts of the musical elements of the system, which is the reactive and generative structures. On the left, we can see an example of a synthesis structure within the system, and on the right, generative control of that structure. This is the chaos drums section. I won't go through this line by line, but what is notable is here, where different pieces of data from the neural network and from the derivation stages enter the synthesis structure, thus making changes to envelope, pitch envelope, and here we have an FM-based feedback system. There's also reactive control to the generative part of the structure. Here we have sensitivity to its amplitude of the audio. I call Mudfish a simple reflex agent based on the fact that it only really responds to current input stimuli. It has no meaningful understanding of precept history, using only one control period of 1,024 samples to do feedback and parameter updating. I call this ML informed, but not intelligent. Looking ahead, I'm interested in what additional AI and machine learning techniques can bring to the world of new musical instrument design. I'm curious what a more complex neural network might sound like. I did hit various CPU limitations because of the Bella Mini microprocessor. For this reason, I might move this to an in-the-box approach, that being a pure software approach. I'd like to upgrade the enclosure, as you likely noticed in the video. There's some fogginess on the sides. It looks like fingerprints. It's actually damaged from when I laser cut it. The sides are also open. We see the computer spilling out of it, the various wires. This is perfectly functional for this project, but I would like to close that in at some point. I'm curious what it might mean to build a guitar pedal out of this or a synthesizer module. And in this way, I'm curious what a commercially viable product might look like. At this point, I'm ready to take any questions.